Hi. So I see there's 4 people in the room. I suppose we'll have to start because I have another class immediately after this one. So, okay. I'm just going to quickly share my screen. And then maybe we can start. Just wanted to start off by, because I do hope people have gotten those emails we sent, the most recent emails, and specifically is to do with, I guess, a scheduled assessment. That's a class test. And we've decided to schedule it. This is tentative, but we've decided to schedule it for the week of August 3rd. So it's likely that the test is going to be on any one of these days here next month, right? And the reason obvious is because the exam is apparently 2 weeks immediately after that week. So I think exams start on the 17th or something, which is a Monday. So there's that. And then the other thing is we went ghost here, we went silent because it's been a bit hectic. And so we decided to stick to the normal IDE schedule. And we're actually secretly hoping that you guys were going to physically come through for residential school, but it appears that's not happening. Which is why we just decided to schedule these events during this so-called residential school. Apparently, the residential school is supposed to go all the way up to end of July or something. So there's that. And I see Pierre is in the room, I think. Pierre, feel free to chip in if you need to. And then we haven't really had any assessments per se. But we're planning to have one major assignment, which is going to, I guess, incorporate some aspects of what you're going to discuss with me. So that's modules. Also the, I guess, the assignment is mostly going to come from module 2 and 3, and then combined with what Piela is going to cover in module 4 and module 5. So we are hoping the assignment to be ready, I think, by the time Piela is done. Hopefully, Piela had mentioned that he's planning to work towards his portion, I think, beginning next week. Which is like Monday, I think, I don't know. So in fact, that's one of the reasons why some of the events haven't yet been scheduled, because PLA is supposed to schedule those events. So there's that. Right. So my plan is to just run through modules 2 and 3 today and tomorrow, which is why I scheduled blocks of 2 hours. But if it turns out that we don't manage to finish by tomorrow, then I suppose we'll have to sneak in a day, maybe at some point next week or something. I know you're busy people, so we'll just have to take a chance because my Mondays are quite busy. I have scheduled interaction with the 5310 ID course on Monday. So if it turns out that we don't finish tomorrow, then we'll probably have to have an interaction on Monday or something. But that interaction will unfortunately have to be before 17 hours. So it will mean like 14 to 16 or something, or somewhere around 12 to 14 or something. But we'll see what happens by tomorrow. Right. So again, just you should be able to expect like an assignment that you're going to work through by week after next after PLA is done. It's going to be a really trivial assignment, in my opinion. So, okay. Unless if there are questions before we start. The last. Oh yes, hi Pierre.
Hi. So I just wanted to mention. So the interactions that I'll be doing before the modules 4, 5 in the coming week, as Lighton has mentioned, but ideally it should be after he has done the module 3. So earliest will be Tuesday, but I believe I will, or we will let your class rep know for the sessions that are coming. I just wanted to mention.
Right, thanks. Okay. All right. So I don't know if you can see my screen. I do hope you can see my screen. So module 2 is just maybe beam up. So module 2 is essentially database systems, I believe. And right, so today I'll just attempt to gloss over this, and then tomorrow we'll look at SQL, I suppose. Okay, so just to try and, I guess, give an idea of what we're going to talk about today. Very basic. We start with just looking at, I guess, the main motivation why so-called relational databases, and in fact, database management systems came onto the scene, right? And usually the motivation is best explained from the perspective or point of view of systems that were used before databases came into the scene. So that will be your file-based system, which is where we're going to have a broad definition, a broad discussion of file-based systems. And then we'll try and contextualize so-called database management systems from the perspective of what was introduced to us in the screencast that were shared. That's computer-based information systems, because it turns out that database management systems are nothing more than a type of computer-based information system, right? So all those 5 elements that we brought out in module number 1 apply to database management systems, right? So the technology layer, right, the hardware, the software, the data sources, the communication infrastructure. Can't remember what else. And interesting enough, and the data sources itself, right? So there's that, and then the layer that is usually presented at the bottom of that block here, that's the PIP and the procedures. They all come into play. Although another way of looking at module 2 and module 3 from the perspective of computer-based systems here is from the point of view of that one block called data sources, because it turns out that the fundamental role that these databases, right, play is the role of them acting as data sources. Now, you will notice during our discussion, I hope you're able to pick this up, that it turns out there's a difference between a database and a database management system. A database is nothing more than just, I mean, if you look at it from the perspective of information systems or computers, it's nothing more than a file which is used to store the data, right? A database management system is an application software that you use to interact with the file itself, right? So I hope that comes out. And then we'll wrap up today by just looking at the so-called entity relationship modeling, just to have a feel of the process of the things that need to be done before you can actually implement a database, right? So you need to plan. And part of the planning process involves you coming up with what they call an ER diagram, or an entity relationship diagram. And for you to do that, you go through a process called entity relationship modeling. And please feel free to interact with me if you want to in the process, right? So this is precisely what I was talking about here, right? Again, to remind us that I guess this is like a textbook definition of computer-based information system. It's nothing more than a well-structured combination of those 5 aspects that I was talking about. So people, hardware, software, communications infrastructure or communication network, and data sources. And collectively, these 5 elements are used to do certain key things. You use these elements to collect data, you transform the data into information, right? Because data is typically, once you collect the data, it's typically, it's messy, right? You wouldn't really be able to make use of it in its raw form, so it needs to be transformed, right? Once you transform it, you get information, right? And then the information is what is typically disseminated in an organization, right? Right. So in terms of the technology layer here, which is where the databases come into play, you're saying the technological infrastructure is composed by these 5 elements here. And this is precisely what I was saying when I made mention of the fact that we should make a distinction between a database and a database management system, right? So if we look at what we're going to talk about from the perspective of a database, it would fall in this particular block here, right? Because it's a data source. But if we were to view what we're discussing from the perspective of a database management system, then that database management system encompasses all these 5 elements here. Why? Because a database management system is a computer-based system. It's no different from these other types of computer-based systems that we talked about in module number 1, right? So same things apply when you talk about Astria, for instance. When you're talking about Astria or this UNZA student information system, all these 5 blocks apply, right? You need a piece of hardware, you need software, right? You need a communications infrastructure, because it's almost always the case these days that the interaction with computer-based systems such as database management systems or applications like Astria, for instance, the interaction will take place over a computer network, right? So if interaction with a piece of software or information system is taking place over a computer network, you need to have in place a communications infrastructure. Almost always the case is communications infrastructure comes in the form of the computer network. And again, we gave examples of various types of computer networks, right? So if your application, if this database management system is running on a local area network, then the network nodes on that local area network would have to be connected in a certain way, right? If this web-based application is like Astria, which is accessible over the internet, then you need to make sure that your communications infrastructure facilitates that sort of communication, right? Okay, and again, to latch on to, still latching on to what we introduced in module number 1 here, this idea of data and information becomes important. Now, we went through a very thorough process of outlining how data is converted into information and how we generate so-called knowledge from information. And then there are certain schools of thoughts that have asserted the fact that you can actually generate wisdom from knowledge. Of what this is somewhat an idea that is contested. I mean, there are other people that seem not to buy into this, but that's besides the point. That they're not there. Right. So again, this applies to databases or database management systems, because essentially, when you're working with a database, the first thing you do once you've implemented a database, once you start using it, is you collect data, right? From the collected data, you start extracting information. And in fact, tomorrow we'll see exactly how people get to extract information from databases by running so-called SQL queries. This is where that structured query language comes into play. Suffice to say that there are other operations that you tend to perform besides just querying for information, right? Obviously, before you can query information, you need to add information to the database, right? In certain instances, once information has been added to the database, you might want to make modifications, changes, in the event that there's an error, for instance, right? So we'll see how SQL comes into play. Even better, there are instances where or when you might want to get rid of information that you've inserted into the database, right? So we'll look at, in fact, tomorrow's discussion is broadly centered around just 2 key aspects of SQL, so-called data definition language statements and data manipulation language statements, DDL and DML. Sorry, I had to admit David's there. This is making sense. It's just a revision of both screencasts that were shared last month and the month before. Right, again, same thing I was talking about here, but represented in the form of the so-called knowledge hierarchy, right, where the raw facts are at the base and then you have wisdom at the top here. All right. Again, just a reminder that when we're making reference to these things we're calling raw facts or data, it's nothing more than just bits, right? This is actual information that the computer gets to work with, right? And again, in the batch of lecture screencasts that were shared in module number 1, we went through a process of briefly outlining exactly how the computer gets to process this information. That has nothing to do with computer-based information systems per se, but we are just trying to outline exactly how hardware and and software, or the role that hardware and software play insofar as the processing of these raw bits is concerned. Right. The remainder here is just the textbook definition of information, knowledge, and wisdom, really. Right? But key takeaway point here is that we derive information from data, knowledge from information, and then wisdom from knowledge, right? Combined with a bit of domain expertise, obviously, and experience. Just a quick rundown of what was essentially outlined in module number 1, because it turns out, again, that module number 1 is linked to almost everything that we're talking about, right? Once Piela starts talking about module number 4, for instance, where you look at a specific case of the relational database management system, that's MySQL, to notice that what you'll be discussing is like an instance of the so-called relational database management system, right? So it's just a case study. That case study could just as well have been anything else other than MySQL. So it could have been SQLite, or it could have been Access, for instance, or maybe PostgreSQL, for instance. Okay. Right, but all of those things, right, can be linked to computer-based information systems. Okay. So like I said, prior to so-called database management systems, right, DBMS is here, data was traditionally stored in flat files, right? So these flat files are what are referred to as, they make up what's referred to as a file-based system. So a flat file could be anything that's akin to, let's say, these text files that you create using Notepad, for instance, right? So you create a .txt. You can view a flat file as being something that's similar to like a .txt file, right? Where information is just it's stored, and it's called a flat file because there's usually no structure, right, associated with the information. Yeah, but it doesn't necessarily have to be a TXT file. It could have a completely different extension. But I guess another way of looking at this is that instead of storing data into a well-organized collection like a database management system, what you're doing is you're just dumping the information on the file system itself. And it turns out that the way file-based systems work is that they provide an almost one-to-one mapping between what you typically find in so-called paper-based records, right? So this screenshot here just shows you a very basic record. This is from property, a real estate company of sorts, I think. Yes, I think so. So you notice here that if you were to create a mirror of what you're seeing on this image, this is from like a paper-based record. Creating a mirror of this onto a flat file just involve maybe you just creating a TXT file and then just providing labels with corresponding values inside that particular flat file. And obviously the mapping was done to just automate this process. It's like a one-to-one translation from paper to electronic form. And we still see these things, I guess, these days. Shockingly enough, the last time I went to Unza Clinic, which was, I do believe that was 2017, I think, or something, 2018. Because I hadn't been there before. I mean, the last time I was there was when I was a student. They brought out this so-called card, right? And then they write down my details. I hope at some stage they transferred my details from that paper-based record to some electronic format, which likely, if that's the case, which likely is actually in the form of a database management system, right? So my information is probably subsequently transferred from a paper-based record to electronic format into a database, right? Just speculating, but that's likely the case. I'll be surprised if Unza is exclusively making use of paper-based records. But key takeaway point here is that file-based systems were essentially nothing more than, a mirror of what you'd see on a paper-based record. Now, if you pause and think about this for a second, you realize that and most of these probably drawbacks of so-called flag files. You realize that there are certain drawbacks that you can immediately notice, right? What we're going to do is focus on things that can be linked to what database management systems do better when compared to file-based systems, right? So you immediately realize that if you're using a flat file, it becomes extremely difficult for you to separate data, right, to isolate data. And this idea is best explained by using an example. When I go to a hospital, right, or when I went to Unza Clinic, if I have an illness that I don't want other people to know about, it becomes difficult when you're using a flat file, right? Because all the information is just stored in that one record, right? Essentially one file. So whoever has access to that file typically be able to know everything there is about me, right? My entire medical history, which in certain instances I might not want people to know about. If we draw parallels with your situation, for instance, if UNZA was using a file-based system to keep student records, right? I'm assuming that the entire student record is just one file. You realize that it would be difficult to separate your financial details from your academic records, from your personal records, right? Because once you know at the UNZA, what the UNZA does is they collect massive information about you. So they have information about where you went to school, details of your so-called next of kin, your entire financial records from the time you enrolled at UNZA in first year, the grades that you've been getting. Now, there are certain people that might not need access to things like your financial records, people like Lighton. There is no reason why I should have details of your financial record. Why? Because my role at UNZA revolves around academics, right? I may need to have access to your grades, but certainly not your financial records, certainly not your personal records, right? Why would I need to have access to your phone number? Right, so you notice that when you're dealing with file-based systems, isolating data, and especially sensitive data from non-sensitive data, becomes difficult. Specifying which entities will need access to specific portions of a particular record becomes difficult. But you will soon see that with databases, you can ascribe roles to individuals that have access to a database, thus restricting access to portions of the record that certain people do not need to have access to. So for instance, if you look at SIS, you might not see this, but behind the scenes, when you're accessing SIS, your information is in a relational database management system. When I'm accessing SIS, my profile on SIS only allows me to have a view of academic records of students that I enrolled in courses that I teach, right? So the only academic records that I have access to when it comes to your records are just restricted to 3010. It makes sense if you think about this, right? There's no reason why I should have access to, I don't know if there's 3020, I don't know if you have a 3020 course or something, but I'm just reaching here. So separation of concerns, right? And then the other thing here, the other problematic thing associated with file-based systems is the issue of duplicate data, right? Duplication of information. Again, just to latch on the same examples I just talked about here, if you look at this record, for instance, you will immediately realize that in the event that you have, let's say, 100 leases, right? And this was in a flat file, you would need to have 100 instances similar to this. Now, if you have 100 instances similar to this, and I'm trying to see if we have a classic example here of something we can latch on to, probably bad example of duplicate details here. This is a horrible example. But Imagine, let me see here. A horrible example. Let me see if I have another example here. Probably not. Okay, imagine a situation where this was your record, right? The student record and not this document that we have. And that record, aside from like your personal details, you have access, I mean, you have details associated with, let's say, courses that you're taking with corresponding details of the lecturer details that are taking that course. Now, if you think about this for a second, if you let's say you had lecturer details as part of the information that you're putting in the flat file, what that means is that the details would have to be replicated 100 times, assuming that we had 100 instances of this record. The problem with that is that you are duplicating details of lecturers in all these different files. Now, you probably sit there and you're asking yourself, oh, but what is the problem with that? Well, the problem can be perceived from so many different angles here. Number one, you'd end up using more space, right? More space because you have the same information replicated in 100 different files, right? So that's the first problem. And the other issue here is that in the event that you want to make a change to information that you're duplicating, you would have to make those changes 100 times. You will soon see that with databases, you can actually take advantage of certain database management system features that enable you to just change a record entry or data once, and then all the changes will be replicated throughout the database, right? So that's duplication of data. Mostly this is linked to space usage and I guess the difficulties in being able to make changes to record details that have already been specified, right? So if you're wanting to update a record, it's likely that you'll have to make the same change multiple times, which is error prone if you think about it, right? What are the odds that instead of you propagating that change to all the 100 records, you miss out maybe 5 of the records, right? Just because you have to do it over and over again 100 times. And we're simplifying this whole thing here because it turns out that there are ways of automating this whole process of updating records such that you avoid errors, right? You can literally come up with a script, but that's besides the point. The key thing here is a drawback of file-based systems is duplication of data. Okay? And then there's also this whole notion of, and I guess I already made mention of the dependencies that exist because you have to make changes multiple times here. Right? And then finally, you are restricted to fixed queries that you can use to access information from the data. Because remember, irrespective of whether you're using a flat file, a file-based system, a database management system, ultimately what you're interested in is to be able to extract information from the raw facts. Right? One way, the way that you extract information is by coming up with so-called queries, right? A way of accessing what you want from whatever system you're using. The disadvantage or the drawback with file-based systems is that you have a set of just fixed queries that are just tied to the structure of the record here. Right? So extracting information that is linked to multiple types of files associated with the records becomes a bit of an issue. But with database management systems, and specifically relational database management system, it's extremely easy, right? With so-called SQL, or structured query language. Right, so some really drawbacks of systems that were used prior to the introduction of database management systems. Right? So it turns out that, like I said, this was the motivation for introducing database management systems, and really, you immediately see that once you will see, hopefully today or tomorrow, those of you that have already gone through these notes here, that you'd have already understood that with database management systems, access to the data and manipulation of the data becomes extremely easy, right? And you can easily control things like access, especially, and who manipulates the data. With a flat file, whoever has access to the flat file can make changes to that thing, right? If they have right access to the file. But with a database management system, you can restrict access, right, through the use of roles. So for me to be able to modify your grades via SIS, I've been given certain access privileges, right? So I'm assigned a role, and that role has certain privileges that allow me to modify or to make changes. So you can easily control access, which is a good thing. Again, if we were to latch on to examples of like a hospital, for instance, the nurse doesn't need to have details like details of my medical history. Why? Because I don't think she, or her role is just maybe depending on what the nurse does, I suppose, maybe to inject me or something. So she doesn't need to have access to my entire medical history, right? Perhaps only the general practitioner who is attending to me or who attends to me needs to be given access to those details, right? With a database management system, you can easily control access. And controlling access comes or is done in so many ways. In certain instances, views are used, right? So-called database views. Usually it's database views, actually. In certain instances, depending on whether you want someone to just have read-only access or someone to have write access, all you have to do is just flip a switch and say, these particular users or users with this role can only read information from the database. They cannot make changes. So for instance, administrative secretaries, for instance, the administrative secretary in the LIS department, if you have an issue and you visit the office, it's likely that I think she has access to SIS. She can easily log in and just try and verify certain details, right? But she cannot make changes, right? Lighton will likely be given access to modify grades associated with LIS 8010, right? I will not have, there's control over these other courses. I will not have access to to make changes to grades associated with these other courses that I don't teach. In fact, I don't have access, read access to those details, right? So I have no idea what sort of grades you've been getting in these other courses. And it makes sense, right? Security is important. All right. And then the other advantage linked to database, and you notice that most of these advantages I'm talking about are flipped over versions of some of the drawbacks of file-based systems, if you think about this for a second. The other beauty with database management systems is that the data definition itself is embedded within the application you're using. And in this case, it's the database management system. Rather than storing these things separately. And I don't know if people are still there. It's quiet. I don't know if it's just me. So I'm just going to pause for a little while and just try and ask if people are following through.
We are following.
Okay. Are there any specific questions? Or is this just, this is easy stuff, right? This is all making sense. From experience.
I have a question.
Yes, please.
Okay, the last point where you're saying the definition of the data is in, maybe if I could just have the presentation again.
Oh, right.
Your screen.
I was trying to see,
I
was trying to see who was talking. Yes.
Okay, so this part, no, this is Wedson.
Yes, yes, I was trying to see the name. I saw your name. Thanks, Wedson.
So the definition of the data is incorporated within application programs rather than being stored separately. This is the one you're saying is a flip over of the other one where you say the...
No, I was actually saying that if you think about it, most of what I was talking about here, we're just talking about the things that databases do better in relation to what file-based systems do not do better. Yes.
Yeah, I get that part, but what I don't get, or maybe the explanation that I haven't really captured, is if you were to take it back to the previous slide,
yes.
This same point, last point, fixed queries for specific applications, it's somehow related to the other one, in that you can flip this one and it becomes an advantage for the other one. But the explanation, or maybe what this really does, is what I haven't captured.
What do you mean by, sorry, could you rephrase the question?
Okay, for starters, you said separation and isolation of data is hard, like on a file-based system.
Yes.
Yeah, I've gotten that explanation in the sense that if you were to refer to a specific kind of information, it's difficult for you to to separate information. In that,
Yeah.
if somebody has access to that file, they'll be able to see whatever is the contents of that file. You
Yes.
can't restrict to say they can only see this part. So
Right.
long they have access, they will see the entire thing. Then, for the database systems now, you are able to restrict access. You can set profiles for the levels that somebody can access.
Right.
Yeah. Now the last part, you've said fixed
Fixed
queries
query.
for specific applications. This is now the explanation that I haven't gotten.
Okay, so with databases, because essentially what in fact, when you look at this from a perspective of relational databases, what you do is you store data in such a way that it's linked with each other, right? So if I was to give, this is best done by using examples here. If I was to use an example of student records, for instance, with a database, you would have details of is it student grades stored in a separate table, right? Details of student financial records stored in a different table. But all those different tables are linked to each other. And usually the linking is based on like a key that uniquely identifies the record. So that would be like your student ID is what links information stored in these different tables. So you immediately realize that extracting information becomes a lot easier because all you do is you just link, or depending on what sort of information you want, you're able to link those different tables together and extract the information that you're interested in, essentially making it possible for you to come up with custom queries. That with a flat file like this, it becomes, you're only restricted to a limited number of queries because the structure is fixed. You just have access to this data dump. And so extracting, I guess coming up with customized queries becomes a bit of an issue. Although, I mean, people would argue that you can, with a little bit of extra effort, actually, you can do this, right? You can come up with custom queries. Maybe the best way of looking at this is that it's difficult for you to come up with custom queries with flat file. I don't know if I'm answering it, if that answers your question. Essentially, with databases, you can easily link together different tables, right? If we're looking at relational database management systems, and be able to selectively pull out what you're interested in. So if I'm interested in querying financial records for students, right? All I have to do is link, I guess, a table that has demographic details of the students and the table that has financial records, and then I'll be able to pull that information. With flat files, that would be somewhat painful here, right? Another way of looking at this is queries like, oh, how much money did the ONSA make in terms of payments coming in from IT students, for instance? With a database, you notice that you will see tomorrow that all you have to do is just write a simple SQL query and then you'll be able to pull that information, right? You aggregate the information you're interested in. But with a flat file, you'd have to come up with some really complex script for you to be able to do that. So I don't know if I've answered your question or if I still have not, or if I was making sense here.
No, I have gotten the concept.
Okay. But maybe, again, for some of these questions that you have, if you ask a question and it doesn't make sense, we can pause it, write it down, pause it, and then see if it will make sense once we have our brief discussion tomorrow. Because it turns out that most of what we're talking about tomorrow is more hands-on, so you're able to, you'll be able to put to practice some of these things we're talking about, like you'll be able to see exactly how easy it is to extract information. And I'm actually regretting having used having used the database. I came up with a very simple database. It only has 2 tables. It would be nice if so the practice tomorrow is just going to involve this very it's really a real life kind of, it's a real life database if you think about it. We're not working with fictitious data here. This is actually actual data, and it's about, we'll remove some records. It's about almost 2,000 records, and I'm thinking maybe we would have would have been better if we used a more complex structure, right? Complex structures like, let me see if I can, complex structures like, I know I shouldn't have been talking about, but I have to show you this, I guess. No. I have to show you this. Maybe it's nice to veer off slightly here, but let me see if I can, database, so just to show you how, maybe this will as well, maybe this will help address the question you asked, because most of the examples that are typically given in books is like this property tables or student database, which is very simple, right? But it turns out that databases can be complex, right? Can be complex, like your so-called SIS. On the face of it, you might think that, why can't I find that? You might think that it's a simple database that they use, but I would like to think it's complex. In my previous life, I worked with, oh, there we go, this is what I wanted. I worked with, I worked for a telecommunications organization, and I mean, part of my role was to, my purpose in life at the time was just to write SQL queries to extract data from millions of records, right? So when people make calls on these networks, right? When you SMS, when you're calling people, all those details are logged, right? Down from where you're calling from, how much money you're spending, who you're calling, how long you called them, when the call started. And so the databases that we're working with, these were large-scale databases, right? Complex databases. And in fact, you begin to appreciate these things I'm talking about if you look at databases from that perspective. It makes more sense for you to use a database when you're scaling up, when you're handling massive amounts of data. It would be insane for Facebook to decide to say, we are going to store those records about what people are posting and liking and sharing onto a flat file. It would be insane, right? You have to store those details in a database to make it a lot easier for people to be able to extract the information, right? So can get as complex as what you're seeing here, right? So this is like a database that is used to power, these are the tables here. It's used to power applications like the UNZA institution repository, right? So this thing, we are interacting with it and you think it's a simple thing. It is simple actually, right? Once you understand the principles, but behind the scenes, the way the data is structured in such a complex manner, right? So that it becomes a lot easier for information to be extracted from here. I'm just going to share this. You have to look at this at some point. So I'm sharing, that's the UNZA institution repository. The UNZA institution repository, what you see in that repository, part of what you see, that's a metadata record that's stored in there, right? And actually, the complexity of what you're seeing here is, in part, involves not just what you're seeing in the background, but how user access is controlled in the database. I mean, there's more at play here, but fundamentally, right, this gives you an idea. Here's another way of looking at this. The UNZA website, right? It's a Drupal, I don't know what Drupal it is, Drupal 7 database schema. The UNZA website runs off of a CMS called the Drupal, right? Now, I don't know if this is the actual version of Drupal 7 because I know the UNZA website runs Drupal 7. The UNZA website, this thing, when you go to www.unza.zm, you're accessing this is all dynamic content, by the way. This stuff you're seeing here, this is all in the database, right? It's generated on the fly once users are accessing the database. All of this is dynamic content, right? Because this is Drupal CMS, right? The content management system. But here's the thing, Drupal 7, all that thing that you're saying that is dynamic content is made possible by this sort of structure here, right? And really, if you look at it from the perspective of the scale of data that you're handling. Like if you look at the UNZA website, it's so complex, right? It's not just the stuff that you're accessing there. You go here and you're just reading up on, oh, the reopening and virtual graduation. No, there's more at play here. If you go to the schools section, for instance, each school has a profile of a faculty staff, right? UNZA has 854 faculty staff. Each faculty staff is, oh, go to our able leader, right? The head of department. Each faculty staff has associated information about them, right? Their publications, their profile. This all can be changed on the fly. All of this information is stored in a database, right? And you immediately realize that, oh, so this thing, then it makes sense, right? It makes sense that it has to be complex because all this is generated on the fly. It's stored in a database. You need a complex structure like this. Think of what sort of painful process you'd have to go through if this information was stored in flat files, right? It's possible, but interacting with information in flat files would be very painful, I assure you. I don't know if this is making sense or I'm just rambling and ranting about. So I was saying it would have been nice if we used it would have been maybe nice if we used a more complex structure rather than a simple structure which only has 2 tables. But it turns out that it's a lot easier for you to grasp the concepts if you simplify these things, right? In real life, what you handle is like huge databases, right? Huge databases. Anyway, any other questions? On file-based systems and yes, no, is it clear? Was I making sense when I was talking about some of these things? Okay, know what the no answer means. Okay, so jump on to so-called database management systems to see what they're all about. Textbook definitions, I suppose. So we'll start by defining a database, right? Because one thing we need to get out of the way here is that a database management system is nothing more than just, it's a software tool that is used to interact and manage a database, right? I don't know if there was a comment here. Okay. Right, so a database is nothing more than a so-called shared collection of logically related data and the corresponding description of the data. Right, so this is, typically this is a file, by the way. So this logical collection is designed to meet the information needs of an organization, right? And if you seriously think about this or link it to module number 1 here, information needs can be linked to so-called information systems, right, or computer-based information systems. And so fundamentally, you are interested in coming up with this shared collection that will be able to meet your information needs. In the case of Astria, the information needs, we know what they're all about. Managing teaching and learning activities. In the case of the UNZA website, or the database that powers the UNZA website, we know what the information needs are all about, right? Generating dynamic content for the website. Right, so this logical collection of related data here is nothing more than a repository of data that is accessible by different users. In certain instances, it could be a handful of users. In some instances, especially these days, it could be thousands or even millions of users. Like if you think about Facebook or YouTube, for instance, at any given point in time, you have millions of users that are accessing the repository that has this collection of this shared collection of interrelated data, right? Right. So this shared collection will hold the operation data and the metadata as well, right? So I can tie to some of the advantages we're talking about here. The databases will typically allow data to be abstracted, right? It's abstracted in such a way that if you're a user, a database user, you'll only gain access to the portions that are applicable to you, right? The portions that you've been given access to, the portions that you've been allowed access to. And in most instances, actually, people will not realize that the database that they're using to access data is complex, right? Because you have this narrow view of the shared collection. In your world, you think, like in your case, when you go on Astria, you think what you're accessing is just details to do with or the modules that have been uploaded and the announcements. But in the background, there's so much, right? If you look at the view that people from ID have, for instance, you'd be amazed, right? Because what they are interested in is extracting statistics, for instance. For a course like LIS 3010, how many students of the enrolled students, how many are actively accessing the content, right? From the enrolled students in the course, how many have attempted the assessments, if they're assessments, for instance. And you will not see that information, but the people from IDE will have access to that information. Why? Because their view has been abstracted to only include aspects that are relevant to their role. Right? Anyway, the other beauty here with the database management system is the definition of the data can easily be changed without affecting the data itself. And we will see this once we discuss DDL and DML statements. Right, but the key takeaway point here is we are starting off by defining what a database is. The difference between a database and a database management system. Right, and I guess I'll explain more about this just now. So a database management system is a piece of software, right, that allows end users to define, to create, to maintain, and to control access to the database, right? So the database would be a shared collection, and the database management system would be a piece of software that facilitates access to the database itself. Usually the case that end user application programs would be used to interact with the database management system. Now, I know that at this stage, if you're not familiar with this, it gets a bit hazy here and confusing, but it will make sense very soon, I assure you. So typically, when you decide to create a database, you create a database, you will create a database and interact with the database using a database management system. But it's rarely the case that end users will be interacting with the data via the database management system. No. Think of what happens with Astria, for instance. There's a database behind the scenes, but you do not interact with Astria via the database management system. Instead, what you do is you interact with the database management system through an end user application. In this case, the end user application is the same thing we call, Astria. This Astria thing here would be an end user application. When you log into Astria, this thing you have access to, this application you have access to would be an end user application. In between the end user application and the database is the database management system, right? It's kind of interesting if you think about it, actually. Right. I'll give an example once I'm done with this. Maybe it will make better sense soon. So the database management system will enable users to, like we said, to define the database and to manipulate data stored in the database to allow users access to the data, right? Again, fundamentally, all these operations we're talking about here are linked to why you have a database management system in the first place. You want to be able to define structures, right, using the data definition language statements, right? You want to be able to maintain the data, add data, modify data, delete data, right, using DML statements. Again, the database management systems will provide controlled access to the data itself. So like I said, this is a piece of software, right? If you were to link this piece of software from our discussion of computer software in module number 1, where we were ranting about all system software and application software, you immediately realize that a database management system is actually application software, right? Classic example of application software. I hope you remember the distinction between system software and application software here. And so the DBMS application we interact with the database, right? And this is done by issuing so-called structured query language statements to the database. So here's a view here, right? You'd have end users, different types of end users. Depending on their role, they have different views to the database, right? So these end users will typically use an end user application, right, to gain access to the database management system. Right? Clients or end users interacting with the database management system via an end user application. And what they're interested in is to gain access to the data that is stored in a database. I don't know if this is making sense. A database is a piece of file. Observe, I'm just going to, I have open here a database, but this is an end user application, I guess. I have, let me just go to the module. I have this database here, right? This file here. I don't know if you can see this file here, but this db hyphen unza underbar dspace underbar ir.db. This is a database, right? This database, I cannot interact with the database the way it is, right? It's a piece of, it's a file, right? Just like a Word document or PDF document. But for me to interact with this database, right? This file here, which is represented by this component here. For me to interact with this database, I need a database management system. And the database one of the database management systems that I would use in this case is I love SQLite, so I'll use SQLite 3, and then I'll use DB underbar. One of the database management systems that I'm using here is SQLite. This is the database management system. Now, what we were saying before is that I cannot show tables, I guess. Ooh, that could show tables. I wonder what, I've forgotten how to run raw SQL. This is the thing of not running, not using the database like directly, not directly interacting with the database, I guess. Okay, I wonder why this is happening anyway. But that's neither here. Oh, tables, I guess, tables. Right, so you notice that what I'm doing here, right? What I'm doing is I'm interacting with the database using a database management system. The database management system I'm using is SQLite, right? So using this database management system, I can access, hopefully this will work, I guess. I can access data that's in this database, right? By issuing SQL queries like so. But what we're saying is that the average user does not interact with the database this way. You need an end user application. What I was doing here is I was using the database management system to interact with this database here, this file here, right? The average user will need an end user application to interact with the database, right? So you use your computer, like in this case, I'm logged onto my computer to interact with the database. One of the end user applications which we're going to make extensive use of tomorrow is something like DB browser, right? So with DB browser, I don't have to worry about what I was doing there, the gory details of what I was doing, right? All I have to do is load the database, right? And I can actually browse for data. Easy, right? This is data that's stored in there, easy. I can also run SQL queries here, right? I can also run the same SQL queries I was running there, but in this case, the interaction is more user-friendly, right? Because I'm using an end-user application. Now, this idea of end-user applications really is, we're loosely referring to it here. An end-user application can be something like this. This thing that you access when you go to the, oh, I'm going to access Astria. This would be the end-user application. Ultimately, what you're interested in or what you're doing when you're accessing Astria is you're interacting with data stored in a database, right? But instead of interacting with it directly the way I was doing it here, you are using an end-user application. Same goes for this UNZA website. This information you're seeing here, all this stuff here is stored in the database. Well, maybe some things like binary files, like images, are probably on the file system, right? But the same goes for Facebook, right? Oh no, I'm gonna log on Facebook. Also, please send me a friend request if you can. When I'm logging on Facebook, all this information is in the database, right? All of this is in the database. This is dynamic content, right? When oh, maybe I should like, I don't know if, when I like no, I don't know if I like that, but there's nothing to like here. But when I like something, right, on Facebook, all that information, I wonder if there's something to like, I don't know. All that information is stored in a database, and it makes sense because once you like something and you log out of Facebook, you log back in, you will see the fact that you like it. Oh, maybe if I go to Zambian Watchdog. If I go to Zambian Watchdog, right? If I go to Zambian Watchdog and I like, maybe Lusaka Times, no Zambian Watchdog, right? If I go to Lusaka Times and I like a post there, people that log in to access Lusaka Times will be able to see that Lighton liked this this particular, there's also nothing to like. Why is there nothing to like these days? Wow. Well, maybe this anyway. When you see angry people here, it's, well, the key thing, I won't like anything because there's nothing to like. But the key thing here, right, is if I see this, right, irrespective of whether the person who liked this has logged off or on, the details of what they did will persist. So I'm able to see who liked this, who was sad, right? I wonder what that means, or who was angry or something, because this information persists in a database. And I don't have to direct access the database because there's an end user application, nice end user application called, a Facebook app, right? This could be a mobile app, or you could be accessing the Facebook application via this web browser here. But bottom line is, you typically use an end user application for you to be able to interact with data, which you store in a database. End user application gives you access to database management system. Database management system is used to interact with the database. So if you look at this, it's a 3-tier kind of architecture here, right? I hope that makes sense. Again, this is what I said from the onset when I was trying to link database management systems to computer-based information systems. In fact, database management systems are nothing more than a type of computer-based information system, right? You need a piece of hardware for you to be able to install. I was able to install this SQLite database, relational database management system, right? This one that I accessed here, because I have a piece of hardware, which is my computer, right? So I have hardware, right? I'm able to make use of this database management system called SQLite. It's a piece of software, right? It's a piece of software, but also, even more importantly, before I install this piece of software, I need to have access to, I need prerequisite software like an operating system software, right? I just can't install SQLite. I need an operating system, a computer with an operating system. So I need software, right? And then also there's data, right? The data is the actual information that I plug into this database, right? So these things that I was querying here, this information that I was accessing here, right? You typically would need procedures, right? Now, all of this is the technology here. You need procedures. The procedures would include things like details to access rights. Who will have access to financial records of students? All the people in finance, maybe the HODs, because when students have a complaint, the first place they go to is the HOD. Maybe it's assistant registrar or whatever that is, right? But the key thing here is the organization will need to come up with procedures on how data is going to be accessed. And of course, you have people, right? So there are people that are going to be accessing the data, right? People that are going to be managing that data, right? The behind the scenes, the system administrators, or the people that are backing up this data so that in the event that something goes wrong, you can easily recover, right? Key thing here is that this thing we are calling a database management system is a computer-based information system, essentially. You have all those 5 aspects that we talked about. I hope that makes sense. People always say, we want advantages and disadvantages. Well, we've already mentioned some of these, but to just explicitly put them out there, getting rid of redundancy, right? And we highlighted this when we were comparing database management systems to file-based systems. The data is more consistent because you have a situation where you only update information once, right? Not multiple times. We'll see this in action tomorrow. You can easily share people by controlling access. So you can easily share data by controlling access or by giving people controlled access to the database. And then obviously there's improved access here, right? Now, nothing is perfect in life, there are disadvantages, and I'm sure you've already seen the disadvantages, right? There's so many different moving parts when you're dealing with a database, especially large-scale databases, right? So the complexity is usually one of the, I guess, one of those disadvantages you want to cite, right? And which is why you have to carefully think things through. Not every piece of information that you handle as an organization needs to be put in a database. Oh, we have files that we are compiling. Well, you can put the files in a database, but if you have the files in PDF files, do you really need to put those things in a database? Maybe not, right? Because of the complexity, right? Again, depending on the size of the massive amounts of data that you're handling, the size of the data that you're handling or that you're putting in that database, the components, the software components and hardware components that you'd need would be significantly greater, right? So you typically need a lot of computing resources, for instance, if you're handling large-scale data like Facebook, for instance, like UNZA's SIS, right? Because SIS right now has records associated with what? Currently, UNZA has apparently 30,000 plus students, right? So if you're handling data at that scale, you realize that the components, right, the software components that you're dealing with and the hardware that you need to be working with has to be complex, right? Reliable. That means money, right? So you cannot, SIS, the database that powers SIS is not installed on an application like, I'm sorry, on a piece of hardware like my laptop right now, which is like, my laptop has what? My laptop only has 12 GB of RAM. It's not, it's running, or it's installed, or it runs on a server computer system. And we mentioned different types of computer systems in module number 1. Microcomputers, embedded systems, right? Server computers and mainframes and whatnot. So depending on the sheer size, again, you'd be dealing with complex software components and, I guess, hardware infrastructure that has significantly larger computing resources. So by software components here, we are making reference to the database management system itself. SQLite is perhaps one of the simplest types of relational databases that you deal with, right? It's lightweight. In fact, it's so simple that it's mostly used in these mobile applications that you work with. So most of those apps that you install on your phone will typically be powered by a database like SQLite, right? Small little files you're handling. Let me just give you an example here of the size. This data here that I was querying here, this information in here, all of this, right? These are thousands of records. The size of the file where I'm putting this data is 1.4 megabytes. All of that is compressed into, it's put into this file that's 1.4 megabytes in size. But when you're handling massive amounts of data, you would not use some simple relational database management system like SQLite. You'd need something more complex, right? So the UNZA website, for instance, uses MySQL. I think by default, Drupal uses MySQL. You can't use SQLite, right? Now, because a database management system like MySQL is slightly more complex, you typically need experts to be able to manage that piece of software component, right? Not only that, the other prerequisite software components that are required for you to install MySQL more complex, right? So it's likely that I guess the operating system that you'd be using is like something that's like a Unix-like operating system and not your normal Windows 10, for instance, right? So disadvantage, the size of the software components and hardware resources that you need. But also, big one here is the cost with the software and human resource. UNZA has a unit called CICT. CICT probably has, I don't know if people are aware of this, but CICT probably has maybe more than 20, I guess, right? More than 20 faculty staff, I think. Could be wrong here. I think it's more than 20 faculty staff. I hope all the staff are here. CICT, where are you? Part of what those people do is they manage databases. Their role in life, sad as it may be, it's not sad, but they're employed to look after the software components because they're complex, right? They're not here anyway. Not all of them are here, but there are a lot of them, 20 plus, almost 30 actually. And I can't remember which one of these different departments actually is responsible for database management and whatnot. But the key thing here is the cost of the software, cost of the hardware, because you typically need server computers. Server computers are more expensive than microcomputers, right? Or than embedded systems. In certain instances, the type of relational database management systems or database management systems that you use are not freely available. You need to pay money. So I don't know if people have heard of, Microsoft SQL Server, for instance, or Oracle. You need money for those things, right? Those are expensive software components, complex, but explicitly implemented to handle large-scale data, right? So cost is a big one here in terms of disadvantages. Okay, I don't know if people have questions. I thought we'll just quickly look at some application domains. Is this making sense, by the way? Don't know if I'm even online, but I imagine PL would probably reach out to me if I wasn't online. But so in terms of just some example application domains, some of these I was ranting about previously. So the average web application that you interact with out there is database driven. Most of those apps that you work with are database driven. So most of these websites could be the University of Zambia, Zekas University website, State House website. These are all powered by so-called content management systems, which are fundamentally database driven, right? Shameless plug here, my blog, which I haven't updated in a while here. This is running a CMS called WordPress. It's database driven. Behind the scenes is a MySQL database that powers this. This is Drupal, by the way. The Unza institutional repository is database driven, right? It's powered by an application called DSpace, right? And by the way, DSpace has that complex structure that I showed you, right? Where you have a number of database tables that are interlinked with each other. SIS is database driven, right? All this information that you access when you're logging on to XIS, I want to check my results, are they ready, right? All that information is stored in a database, right? The database that has controlled access to it. And you're given the view depending on what you need access to. So in my case, for instance, I might have access to student records, but if I click view fees, I will not have access here, right? Because I only have controlled access. So in this case, you notice that I was logged on as me, which is why I'm able to see the things that you cannot see when you log on to as SIS. Some of these things, I'm guessing you cannot see here, like this feature is probably not available for you. Maybe not, maybe, right? But because my profile enables me to have access to these things, I can interact with SIS like so. And what I'm doing when I'm interacting with SIS again is SIS is an end user application. So this would be SIS. This thing would be SIS. I use SIS to interact with the database management system, but the data that the data that I'm working with is stored in a database. Okay. And these days, really, it would be strange to find an application that's not database driven, right? I'm not sure what sort of applications you use, but these are some examples of applications that I use myself. Now, some of these applications are referred to as cloud-based applications, and so the data may not necessarily be stored on your local device. So it could be interacting with a database that's perhaps somewhere in the cloud, but fundamentally they're database driven. So if you're a fitness freak, for instance, and you track how many miles or kilometers you run on a weekly basis, you probably are familiar with an application like Strava. That information is stored in a database, right? Twitter obviously stores, like most social media applications or social media web applications, we typically store information in a database, right? Granted, these are not, when you're dealing with massive amounts of data, these days it's usually the case that you're using so-called NoSQL databases or graph-based databases, so it's not your typical relational database management system. But it doesn't take away the fact that these days, in 2020, relational database management systems are still the most widely used types of database management systems. Okay, so this was just a simple walkthrough of some example application domains of databases. They're all over these days, right? You can create your own database if you want to, right? If you don't want to use a spreadsheet, if you think that you would want to query data using custom queries, you're better off using a database rather than a spreadsheet. Although these days, you have certain spreadsheet applications that have evolved to enable you to run SQL queries. Like if you work with Google Sheets, for instance, you can run SQL queries in Google Sheets, which is quite useful, really. So I included this because in tomorrow's practical session, we'll quickly go through SQLite so that you're able to run some sample queries here, but just put this here to mention that we're going to use SQLite for this example and an end-user application called DB Browser, right? Which I already showcased here. It has a pretty user-friendly interface. It says point and click here, right? You can literally interact with the database by not running any SQL queries, but it does have a provision for you to write queries, right? Different types of queries, yeah, complex queries, DML statements, and also DDL statements, which we'll discuss tomorrow, right? DDL. Okay, so of course, the other tools that you can use out there. But all right, I hope this was a key takeaway point for this unit 2.3. Here is I guess things like a distinction between a database and database management system, right? Pros and cons of a database management system when compared with their predecessors, which were file-based systems, right? Advantages of database management systems, the disadvantages. Nothing is perfect in life. I don't know if there are any specific questions here. Or concerns, comments.
No, there was a question.
Yes.
Maybe in the chat. I haven't seen the chat. There's a question. Is that we are supposed to download the same applications that you've mentioned, for instance, DB Browser as well as my SQLite. So
it would be nice if you did that because part of at some stage, I think for tomorrow's class, I think there's some things that we're going to be doing, and for you to be able to work through these things, you're better off downloading. Yes, you should, so that you're able to really experiment with some of these SQL queries and to work through some sample problems, right? We have some sample problems here. So it'll be, yes, I think you should, actually. Just like I said, you should download the Dia and all those other applications that I talked about. In fact, what we're talking about now is linked to what I had suggested that you download last time, interrelationship modeling, right? So yes, I think you should download that, yes, so that you're able to practice the queries.
By any chance, can you just provide us with the links on the chat?
Oh yeah, sure. So the Astria's coach site has all these slides. I uploaded these slides, and in all these, where is that? I thought it was there. Sure. I mean, all you need is this. Check slide number 33 on module number 3 on Astria, but I'll dump this in the chat as well. Also, why can't I SQL? How did I export this? Oh, it's an image. Oh, SQL browser. DB browser it's called. So I'm just going to. Any other questions? There's also, DB Browser is not the only end user application that you can use, right? When interacting with SQLite. What you can do is you can also download SQL Expert. Is it SQL Expert or something? Where is that? Yeah, SQL Expert. It's like the way to think about this, right? It's like what do you prefer to use? Do you prefer to use the Facebook mobile app or the one? What is that other app that the normal Facebook app, or do you prefer to use the I thought I had it in. So there's one which allows you to
Right.
use less. Yes, thank you very much. Yes, so those are all end user applications. So the same goes for SQL, DB browser or SQL. Oh wow, SQL Expert. I didn't know. I don't know if it's still there. Download. Or if you want, you can use SQL Lead Expert. These are all just end user applications that you can use to interact with the data, because what we're going to be doing tomorrow is just interacting with the data really, or the database, right? But I will be using DB browser. So if you want to follow through with most of what I'm going to be doing, then you probably want to download DB browser. If you want, you can choose not to download any of them, and you can use SQL Lead the way I was using it here on the terminal, right? It's one and the same thing. You're accessing the same data. Oh, where is that? I thought it was here somewhere. Maybe I'll need to. You can SQL Lead. You can DB browser. If you want, you can interact with it, use it by doing what I was doing here, and but I mean, you probably need to be familiar with stuff here. So say describe. I want describe. Anyway, oh, maybe it's schema, right? Is it schema? Yeah. So I mean, so if you know your way around interacting with the DBMS directory, you can do what I'm doing. You don't have to download DB browser, right? So you'd be in this case, I'm using the, again, there's an embedded. You can view this terminal application I'm using as being a lightweight end user application that I'm using to interact with database management system itself, right? But it comes bundled with SQLite itself. And so, sorry about that. So to tell someone who was calling here, they don't know that I have class. I do apologize for that. I should have put it on mute. So if you know your way around this, you don't have to use DB browser, and let's see, you can interact with SQLite like so, right? Or maybe, yeah, I don't know if that's making sense here. Count the number of records. We'll look at how all of this is, but so yes, we download that, and then so that tomorrow we play around with SQL. It's not that hard, by the way. The beauty with you will soon see, and we were talking about this just now, you will soon see that the beauty with relational database management systems is that they are a mirror of what we are used to. Spreadsheet applications, right? Rows, columns, yeah? That's what you're dealing with. Oh, if you look at the spreadsheet, the anatomy of the spreadsheet, EDU 1020 now. A spreadsheet, you have a worksheet, a workbook, a worksheet. The worksheet has it has row, it has columns, right? Those columns and rows, right? The same thing with a database, really, a relational database management system. So a database could be your workbook, right? The equivalent of a workbook. A worksheet would be your tables, because when you have a workbook, right? When you have a workbook, you can create, this is a workbook, I create different worksheets, right? These worksheets are similar to your table, right, in the database. And which makes it a lot easier for you to understand what's going on really, because you're already familiar with spreadsheet applications, if you think about this. Are there any other questions, by the way? It's going to pause here.
We can proceed.
Okay. I don't know if you've watched Aladdin. I remember Aladdin, where Karim was killed, right? Proceed, touch nothing but the lamp, right? You can proceed and touch nothing but the lamp here. All right, so our focus for this particular unit is just on entity relationship modeling, and the idea behind entity relationship modeling is linked to relational database management systems, right? Up to this point in time, we are broadly talking about database management systems. The focus for 3010 is relational database management systems, right? And the fundamental idea linked to relational database management systems, this whole notion of relational algebra, right, which is linked to entity relationship modeling. So we get to discuss that right now. Okay, so again, textbook definitions. A relational database management system is a database management system that is implemented or that is based on the relational model, right? So the idea behind the relational model is your data is organized into structures called tables. Those tables are interlinked, but also more importantly, those tables are composed of rows and columns, right? The columns are also called fields. We'll talk about this just now, right? So the columns will represent fields associated to your records, and then the rows will be instances of different records linked or associated to that table, right? But just to make mention of the fact that relational database management systems are not the only types of database management systems. There's a whole slew of them out there. And the type of database management system that you use is dependent on the task at hand. But it turns out that relational database management systems are designed or implemented in such a way that they can handle generic tasks, generic database-centric tasks, right? So, but besides the relational database management systems, you have so-called hierarchical models. Now we can go on and on, talk about this, but I want to draw attention to, these are all the different types of models that are out there. But I just wanted to point out that these days, there's a new breed of database management systems called NoSQL database models that have just popped up, right? So they're called NoSQL because you do not run SQL queries. I don't know if I have MongoDB, so probably not, but you don't run SQL queries per se because of how data is stored. You typically organize data or you view data in terms of documents, essentially. And the queries that you run, are not really, they're not SQL queries really. So anyway, bottom line is our focus is on relational database management systems, right? And the fundamental trait of relational database management system is that data is organized into tables. These tables are made up of rows and columns, right? Your rows would have instances of records that you're interested in storing. Your columns will have fields that are associated to the records. Observe, if you are interested in storing data that has student records, for instance, right? You know that you would have, hypothetically speaking, you'd have at UNZA, oh, student ID, right? Student name. Let's not overdo this here, but year of study, right? Now, if you look at this and you view this as a relation, as being data that is stored in a relational database management system, data will be stored into a table, right? So what you're seeing here would be like the equivalent of a structure of a table. That table will have rows. The rows will have the rows will have records. Let's assume these details are right here. The rows will have records now, usually, okay, this is fine. We have records, right? Right? The rows will have your table, you have the table, data is stored in a table. That table is made up of rows. Each one of these rows is an instance of the record that you're storing into that table, right? The table is also made up of columns. The columns represent units of data or portions of the data that is associated with the records, right? So the data could be segmented depending on the piece of raw fact that you're storing. Like ID is a raw fact, the name is a raw fact, right? Year of study is a raw fact. I hope this makes sense. This is a hallmark of a relational database management system, really. But for you to come up with this structure, obviously you go through a planning process where you identify, you conduct a needs assessment where you identify what exactly you need to do, right? Insofar as the design and implementation of the database is concerned. And part of that planning process requires you to go out there and collect requirements. Now I just put it there so that, I put this there so that you understand the process that leads up to entity relationship modeling, right? So you start off by, if you're designing a database, let's say for an organization like UNILAS, for instance, UNILAS approaches you because they've discovered that you're an expert at relational database management systems, and they tell you, say, we want a database. Before you implement a database, you go there and you collect the requirements from UNILAS, right? So maybe you go to UNILAS and tell them, say, oh, I'm interested in you. Can you give me sample records of maybe student records that you were previously storing on flat files or in paper-based records, right? You talk to different people that would access the database, right, to find out their needs, what sort of information they would want to extract and how they would want to access information, because it turns out that all these different things feed into the planning, the design of the database itself, right? Right, so the way in which you collect these requirements really varies depending on the complexity of the task, depending on the sheer size of this database that you're implementing, depending on the number of people, number of potential roles that would need to be given access to the database, right? So maybe for UNILAS, you'd say, I'll organize focus groups with the finance department so that I find out from the people in finance what sort of needs they would have in so far as the database is concerned, right? Anyway, I just put this there so that we understand what we're discussing next, right? So once you collect these requirements, then you create your so-called entity relationship diagram, right? Now, this whole idea of entity relationship diagram is linked to relational algebra, which is briefly what we're going to talk about here. I'll start with some broad definitions linked to entity relationship modeling. Okay, great. All right, so we're trying to unpack the different portions linked to entity relationship modeling here. We'll start by looking at what an entity is or entity sets are here. So again, for a relational database management system, we mentioned that it's made up of tables, and your typical table will be composed of rows and columns, right? Now, modeling that table is done by viewing modeling that database is done by viewing the tables as entities, right? And an entity is nothing more than an object, really. And if you think about it, most of the time when you're modeling these databases, the tables would represent an object, actually, right? Student table, financial records table, something, right? Anyway, so an entity is just an object, right, that exists and is distinguished from other objects. And your typical entity obviously will be composed of, it has certain characteristics or traits, right? Attributes. So a student entity, so if you think about it, these entities, these objects would typically be, you can identify them or describe them based on the characteristics associated with them. I don't know if I'm making sense here. A student entity, right? You sit there and you think, a student, you do a needs assessment. A student will probably need to have, within the confines of UNILAS, a student will need to have a unique identifier, student ID. A student would, because they're above the age of 16, will probably need an NRC, right? All of those things are what we're referring to as attributes, right? A student obviously needs a date of birth or something, right? So attributes will collectively be used to describe the entity, right? They are also viewed, you can also view them as being characteristics of that object, right, which is the direct mirror of the entity. And then your entity set is nothing more than a group of entities with the same type that share the same properties. So it would be like a set of all students, for instance. It would be like instances of the object, right? And if you think about this here, an entity set, once you implement the database, would be like collectively like your records, right, associated with a particular table or something, right? So fundamentally, during interrelationship modeling here, your database is modeled as a collection of entities, which eventually during implementation would be loosely directly translated to tables, right? So an entity is just nothing more than a table once you do your implementation, really, right? And because an entity is composed of attributes, those attributes would have to be converted into database table columns, right? So if we go back here, if we were to view this during the logical design, entity is made up of attributes, right? I hope that makes sense. No. Right, so just a brief description of the characteristics of this entity or object, which are the attributes. Just to emphasize or to underscore the fact that they help describe the entity, right? So the characteristics would collectively used to describe that particular entity itself. It's just an example of just examples of entities, two entities, the student entity and course entity with corresponding attributes, which collectively will describe the entity, right? So in terms of the course, for instance, you need a course code and a course name or something. In terms of the student, this would be a list of attributes that would collectively describe the student. And typically, when you're deriving these attributes, when you're identifying the attributes, the domain within which this database is being implemented will implicitly tell you what sort of values are permitted insofar as the attributes are concerned, right? So for instance, for student names, because if this database is created in Zambia, you wouldn't use Chinese characters or something. So the values would have to be alphabetical letters in the alphabet, for instance, right? The year of study, right? The year of study can never be a year that is before 1967, because we know that the University of Zambia only manifested itself, is it in 1967 or something? So the domain, the key thing here is that the domain will give you clues on what sort of values are associated to the different attributes. All right, so for a student ID, we know that at UNZA, your student ID can never contain alpha characters, right? It's numeric characters, numbers. And in fact, these days, it's, is it 10 digits, right? I don't know if 10 digits, is that true? I'll pause here, let's see if people are following. Well, how many digits does the computer number have? It's not 10, I know.
It's 8.
Oh, okay. Oh, 8. I didn't know that. There we go, right? So, so it's 8. But so anyway, the domain, right? The domain dictates this, and in certain instances, maybe there'll be specifics that we provided. Like in the UNZA these days, I think they start with the academic year, right? So if you're enrolled as a student this year, you have a 2019 as the first 4 numeric characters, or numeric digits that are associated with your computer number or your student ID, right? So key thing here is the domain, specifies what is permitted. All right, so it turns out that these attributes really, they can be broadly grouped, they can be broadly classified into different groups, right? So you have what they call, I hope there are examples here, you know, there are simple attributes, there are also composite attributes, right? So attributes which are composed by just one value, some attributes are composed by multiple values. So if you have a database that has just a student name, that would be a classic example of a composite attribute because it has a first name and last name. You see this? If we said we had an attribute for student name, composite. If you have address, right? Address will probably have something like the street and I don't know what else here, but the street and the town, like in Zambia, I don't know how the addresses are represented, but the University of Zambia, for instance, would be, oh, it's Greatest Road or something, Greatest Road, PO Box, 379, Lusaka, Zambia, or something, right? So it can be composite or it can be simple, right? It can be single valued or it can be multiple valued, right? And I'm trying to see here if I'm mixing. I don't know if I have specific examples here of. I'm wondering, Piela, if you're online, would you say a multi-valued attribute would be if we had a phone number, for instance? I don't know if I'm mixing up. If we had a phone number and we said you can put both numbers here, and let's say I'm 0977, like so, and then I have 096, like so. Piera, would you say this would be a classic example of a multi-valued attribute, right? Single valued and multi-valued. Simple.
Yeah, so that would count if you had the two numbers like the way you've demonstrated.
So this would be, this is an example of single value, right? Multi-value attribute, right? Because it's a phone number, it's the same attribute, but you know that I guess a student could potentially have two phone numbers or something. But this is all contextual, right? It depends on what sort of problem you're solving, the domain you're working within. But you also have derived attributes, right? Classic example is your date of birth. You do not design a database that has age because age is a moving target. Your age this year will be different from your age next year, right? If you design a database that has age as an attribute, what you'd have to do is every year you'd have to update that attribute. But if you have the date of birth, you can have a derived attribute which is populated based on the current year and your date of birth or something, right? So you can derive the attributes as well from existing attributes. All right. And then still on attributes, it turns out that the attributes can be viewed from the perspective of so-called keys, right? Remember again, we are describing the building blocks of entity relationship modeling here. So your candidate keys will consist of one or more attributes that will uniquely identify an instance of that entity, right? So an instance of the object. So view this from the perspective of records, right? If you have a student record, you typically have one of the fields, right? One of the fields that you will use to distinguish this record from this one, right? The attribute or the attributes that collectively uniquely identify or distinguish the different records or instances of the object would be your candidate keys, right? The primary key would be the candidate key that you choose to uniquely identify each of the entity types or entity occurrence of the instance of the object. So notice, if you are to distinguish between candidate keys and primary keys, a primary key is a candidate key, right? The chosen candidate key that will be used to uniquely identify the entity type or instance of the object. And again, maybe a best way of explaining this is imagine a situation where our simple entity here called student also has NRC. Right? You'll notice immediately here that NRC in Zambia, at least, I don't know about these other countries, in Zambia, no two citizens have the same NRC, or at least we don't expect them to have the same NRC, right? So if our simple table here called student also has NRC and student ID, at some stage you have to decide to say, oh, I have decided, or we have decided to say, we will use student ID and not NRC to uniquely distinguish one over the other. So student ID would be the primary key. But in this case, we have two candidate keys because both NRC and student ID can uniquely identify these entity occurrences here, or instances, this object. Now it gets even better, right? There are certain keys that are composite keys. So these are candidate keys that are composed of two or more attributes, right? So in certain instances, you could have a table that will not have an attribute that you can use to uniquely identify to distinguish other records. So what you might have to do is combine multiple attributes to uniquely identify that particular, or to uniquely identify records in that table or entity occurrences in that entity, right? So that would be a composite key. And all these ideas, by the way, are important when you're querying for information, right? When you're designing a database and later on inserting records into a database, right? I guess we don't really make mention of things like constraints, but you define constraints when you're implementing the database to prevent errors from occurring. So if you create a table with maybe an example we'll do here. If you look at the way, so if you look at the way this table is created here, the table we're calling DSpace containers here, we are saying the container ID will uniquely distinguish one container ID from the other. If you look at this other table, you'll notice that we are saying the identifier attribute is the one that we use to uniquely identify each of these 1,000 plus records here. Let me just identifier. Identifier, need to go back to school here. Right, so for that particular record, you notice that this field here is the one that is used to uniquely identify this. So you'll not find, it's not possible for you to insert a new record, right? A new record that has the same ID as that. And it's possible because implicitly there's a constraint, right? So if I was to attempt to say insert this and then I say values, oh my goodness. If I say values and then I say, how many records do I have here? I wonder. Actually, I don't have to do that insert the way I did. Maybe I can. Do I? No, maybe not. If I say new record, for instance, new record, where is that? And I attempt to install, to punch in this and I apply. Yeah, I get an error because there's a constraint that is created implicitly when I specify that the ID is a primary key. The identifier is a primary key for that table, right? Anyways, so different types of attributes, right? This is not really important. I was trying to link this discussion here to so-called relational algebra, but not that important here. But if you want to view this from a perspective, what we're talking about from the perspective of so-called relational algebra here, is the idea is that we said there's relationships that exist between the different tables that you might have, right? And you can view that relationship as being nothing more than a mathematical representation. But this is not important really. We just ignore this, we'll leave this out. But the purposes of you trying to understand here, mathematical representation of the relationship that exists is represented like so here. The key thing though, right, is forget the maths here. The key thing here is that the relationships that you have or that you implicitly define the relationships between the different entities that you have can be broadly viewed or classified into either one of these three different relationships here. So if you have numerous tables as part of your database, right, or numerous entities, remember we said that the hallmark of databases is that you're able to create these custom queries and whatnot. The thing with relational database management systems is their real power is in the fact that the linking of the different entities or tables is done based on the relationships that you define, right? So if you have a database that has a student table and a course table, for instance, there would typically be a relationship that exists between the student table, student entity, and the course entity. And typically it could be that one entity occurrence or one entity occurrence in table A can be associated with many entity occurrences in table B, for instance. Or one entity occurrence in table A can only be associated with one entity occurrence in table B. Or one entity occurrence in table A can be associated with multiple entity occurrences in table B. Think about this for a second, right? And I think we hopefully have examples here, but we can jump the gun here. If we go back to our example of a student table and student and course, right? Student and course. Think about this for a second. A course, one course is taken by many students. Many students can take a course, right? So you immediately notice here that you have a one-to-many relationship for this particular example, right? If you had a financial records table, and I'm making things up here, financial records table, you notice that the student table, one student occurrence here will be linked to perhaps one financial record here. Now, we're loosely defining this anyway. It could be the case that you have financial records each year, in which case you have a one-to-many relationship. But the key thing is that the relationships that you define in between these different entities can be viewed from the perspective of these three categories here. It can either be one-to-many, one-to-one, or many-to-many relationships. Is this making sense?
Excuse me, sir.
Yes.
Okay, just a thought on this approach that you're mentioning here. So, if, for example, you're the student,
yes,
I update the screen. Okay, so if, for example, you had one student, who in a database, then that database has provision or maybe slots for their student records. You have accommodation. Yeah. Then there are also financial records.
Okay.
What else can we put? What else? Then there are courses also. Yeah. So the relationship that a student is going to have to these entities, or maybe entities that have been you've written here, can we say that relationship is one-to-many? Because that one student, or maybe their computer number, can be used to collect information from all these entities.
Right. I mean, so the thing to think about this is you're saying you're viewing these as the accommodation at different entities, right? This is what you're saying. Yeah. Right? So this is entity one and this is entity two, right? This makes sense. And by the way, the question from Watson here, for those of you that are following, is we've sort of like jumped the gun. This is assuming that you've already gone through this process where you go out there and you've identified that upon doing like a thorough requirements analysis process, you've identified, say, oh, the database that we want will be composed of these entities. Now, after you do this assessment here, this needs assessment or situation analysis, once you conduct this exercise, you'll be able to identify the relationships that exist. Now, I wouldn't be in a position to right now, I can't ultimately say that the relationship between E1 and E2 is one to many. It's contextual. It can be, if you look at this from the perspective of the University of Zambia, for instance, this is a classic one to many. Why? There are students that are not accommodated. Is that not true?
Yeah, it is.
Yeah. So E1 to E2 would be a classic one to many, right? And I'm just making things up by making reference to UNZA here. E1 to E3. If E1 to E3 could be either one-to-one or one to many. Again, it would depend on how you want to implement this as a person who is designing, who's coming up with this entity relationship diagram or entity relationship model, right? One-to-one in the event that records, financial records that you have, you only have one financial record for a student. But this is not possible because we know that you make payments every year, right? Is that not so? And I'm just thinking out, I don't handle financial records at UNZA, but I'm trying to recollect what I used to do as a student, right? When I was registering, I had to pay first. So in that case, I would probably have a financial record each year, in which case it would be a one-to-many kind of arrangement. It's making sense. Another way of looking at what's happening here is that the student record will probably be created once when you enroll at UNZA, that's all. Afterwards, it will just be modified, right? Your details will never change. Your computer number will never change, right? Think about this for a second. Maybe your NRC will never change. Maybe your address will change, in which case someone will log in and just modify the address, right? But fundamentally, this will never change. The record will persist, but for financial records, every year you have a new financial record, in which case it will be one-to-many. Courses change as well, right? Every year you take different courses. One student can take many courses during their stay at UNZA. And notice this for a second here. Think about this for a second. Because entities can be perceived from the perspective of them being objects, it becomes very easy for you to model these relationships. A human being has a height or something, so or a student must have a unique identifier. A student must have an age. A student, I'm making these things up. A student must have a next of kin or something, right? So the way that you come up with these relationships, right, son, is contextual. It depends on the domain you're working in. It depends on how you want to implement the database. You have control over this. Believe it or not, there are certain places out there that would choose to not even model relationships. Like I was shocked this first time I worked for Airtel. There were crazy tables that we had where you don't necessarily have these separate entities. Everything is stored in one table, right? So all of these details, yes, student details, accommodation details, financial details, course details, one string, that one huge table. Why? Because you have massive resources, right? So you don't care about the amount of space that is going to be occupied once you create this structure. You don't care how long it will take once you create it because you have a lot of RAM. It turns out that how you model these relationships has a bearing on how quickly you can extract data, how much space the database is going to occupy, the database tables are going to occupy. Redundancy, right? I do hope that answers your question on relationships.
Yeah, it does.
Yeah, I'm going to suggest, we're almost, okay. It does, okay, great. So one-to-many, many-to-one, I'm thinking we'll probably need another session for this, for a practical as well. So some examples of one-to-many relationships here. This is from one of the prescribed books here. I should have included a link here. Otherwise, this is like classic plagiarism. You should attribute sources, right? So a one-to-one relationship will represent associations between single entity occurrences, right? So this example here is showing you a situation where you have this staff entity and a branch entity, right? In this particular context, right, what this is saying is that a member of staff, right, can only be, a branch can only be managed by one member of staff. This is what this, in this particular context, right? Now, granted, in certain organizations, maybe you could have an organization where a branch is managed by 2 people, perhaps, although I don't know if that's possible. Maybe it is possible. But in this particular context, this example is telling you to say, a member of staff can only manage 1 branch. You cannot manage more than 1 branch, right? Now this raises interesting questions like, oh, what about if 1 branch member leaves? Can you not have a branch member from Kitwe act on behalf of the person that leaves? According to this particular relationship that exists, no, someone else who is not a branch manager in this case would have to act maybe as branch manager, right? One-to-many relationships, this is instances where a single entity occurrence from one entity is associated with 0 or more entities in another entity. So in this particular example, a linkage between staff and property for rent, we're saying a member of staff can oversee 0 or more properties. Classic case of one or many relationship. Same goes for student course. One student can take many courses, right? One student can belong to, oh, sorry, you're a bad example. I was going to say a student can only belong to 1 school at UNZA. Now, because you guys are outliers, you have like double majors, right? But you're not into the Department of Library and Information Science, but you have a double major. That's a bad example. But in an ideal case, for programs that are unlike LIS, you have a situation where a student can only belong to 1 department. In fact, you guys belong to the LIS department, even though your program is a double major, right? Classic case of one-to-many relationship. 1 student belongs to 1 department. 1 student belongs to 1 school. You can never have a student at UNZA who belongs to, oh no, I belong to the School of Education and I'm also in the School of Medicine. That's not possible, sorry, right? And then you have many-to-many relationship where you can have many occurrences being associated with many instances this side, right? So let's see. I'm trying to think of an example of our student example here. Oh, what if, guys, what if we wanted to link, if we had a E5 grades and we wanted to link E4 and E5? Think about this for a second. Many courses can be associated with many grades, results from assessment, right? So many to many, right? Is this making sense? By the way, this has this has a bearing of how you access data, how data is going to be accessed, how you're going to link, different tables together as well. In certain instances, joins are not possible where you have many relationships. Well, it is possible, but you'd end up with unwanted results, for instance, right? Great. So in terms of entity relationship modeling here, so there's a certain I do apologize here. Can I pause for a little while and this has been one of the craziest years with this COVID-19 thing, right? I do apologize for that. Sorry for the break in transmission, but it's always nice to let people know. No. Right, so it turns out that the representation of these entities is done in the same way, right? So the way that you present the entities when undergoing so-called entity relationship modeling is done in a certain way. So your entities will be represented by triangles, right? And the triangles are represented in a certain way. 2 segments, where the top segment is the name of the entity. The bottom segment is composed of so-called attributes associated with the entity, right? So observe this thing here. If we were to come up with the equivalent of our student record, then what we'll be saying here is this is student record, right? What am I doing here? This is a horrible example. So if we're coming up with a student entity, in our case, we would say, why am I doing this when we have, I'm sorry again, when we have this, right? So if we wanted an entity, student entity, right? Student entity. Think of this, what we're doing here as entity, right? Student entity has a student ID. We have a student name. We have NRC. We have date of birth or something, right? So this would be our this would be like our student entity, right? When we're doing entity relationship modeling, this is how you represent an entity, right? And then we're saying that the attributes, if there's a relationship that exists between the attributes, you specify the relationship by using lines with directed arrows, right? So you can notice here that there's a relationship that exists between staff and branch with a directed arrow going this side. If you view the relationship from the perspective of the branch, then the direction will be from here going this side. And like we said that the relationship in this particular example is 1-to-1, right? If you remember, one staff can manage one branch, right? If it's 1-to-1, then you have a 1 here and a 1 there to signal the fact that it's a 1-to-1 relationship. Anyway, rectangle, entity name, attributes, directed arrows or lines that represents the relationships that exist. If it's a one-to-many relationship, it's 1 and then the asterisk, right? Many-to-many asterisks and then 1, right? Here's putting everything together. This is what you would have. Oh, I don't know if there was someone who wanted to come in. Florence is late here, right? Yeah, it is possible, Master Piri. We'll make this available. It's being recorded. Yeah, it will be available. Right, so putting everything together, this is what you would have if you were to stitch together the different entities that you'd have come up with. So let's say you undergo requirements analysis and you discover that, oh, the database that I should implement is supposed to have 1, 2, 3, 4, 5, 6 entities. You write down the entities like so, and then this is how you model. This is how you come up with an ER diagram. The ER diagram will have the entity name with the corresponding attributes, including the relationships, right? Now, again, the thing with this is it's subjective. There is no, you just have to justify. There's no one way of coming up with an entity relationship, right? It's contextual. It depends on how you want to implement this. Now, I know this is a simplified version, right? This is a textbook. This is a textbook example here. What we're going to be working with tomorrow is practicing SQL statements using this simple, this simple database, right? So we have 2 entities, records and containers, and the relationship that exists here is many to one or one to many, right? But just in closing, to remind us that this can be complex, and we saw this just now. We saw this when we gave an example of, where are you? Look at this. Can be complex. Is this making sense? Can be complex. Now, again, depending on how you're representing this, you notice that the multiplicity is not indicated here, right? Like the one-to-many thing is not the actual explicit numbers. But let's see the displaced one. Oh, wow. I don't know where that is, but wow. There we go. Not represented here as well. There are no explicit numbers here. But fundamentally, we're saying that this is how you come up with an entity relationship diagram. And it is from this this particular diagram that you now implement the database. Using this, you now use DDL statements to create the structures, right? So you create tables. You would create a table named metadata schema registry, for instance, with the corresponding corresponding attributes. Is this making sense? Maybe it helped. This has probably helped make clear some of the things you were reading, right, as you are reading on your own, I hope. If not, we can do a recap tomorrow before we transition to SQL. Any questions? Miss Shayla, do you have any question or Evo class trip? Very, thank you very much, very useful. Any question? Shayla? I wonder if she's a Gift, any question?
No question so far. I think we'll do a recap tomorrow. If I find any challenges, I'll be able to ask a question.
Okay, great. So what you can do tomorrow is, if you want to play along with, if you want to, it would be nice if you can do this before we meet tomorrow at 16 hours. Is it 16 hours again? I don't know. If you can install DB browser, it's very easy to install. If you can install it, that would be good, because what I can do tomorrow is I can share the database also, so that you try out the SQL queries as I'm walking you through this. I think that is what we should. I encourage you to do this. Now, if it was face-to-face interaction, we would be sitting in a lab, right? And then we would be walking around. You're practicing this. We are walking around to help out where you are stuck. But because this is remote, there's no residential school here. We'll try and see if we can mimic this. Maybe tomorrow we'll have a separate session or something. Okay, I'll see you tomorrow then. I'm so sorry that I have to run off to this other class. Piela, thanks. I don't know if you have anything to say, Piela, to contribute to some.
No, I think we'll just proceed with tomorrow's session.
Okay, great. Thanks. And yeah, ID is brutal, right? But I think it's okay also to be fine. As in the mode of instruction, ID is brutal. All right, thanks a lot. See you tomorrow. Stay safe. Put on a mask or something. Apparently more people are dying now. Bye.
All right.
Thank you.
Bye.